Hi students and welcome to a new video. Today we're going to talk about multiple regression. What is different in multiple regression? What is different from simple regression is that essentially the same model form, except we're going to have multiple predictors here, not just one. Today we're going to see how stress due to work overload can be predicted by anxiety and depression, right? Both. So first thing we need to do in multiple regression, we need variables as our independent and dependent variables. Okay, so here the levels of measurement must be scale, which is here, which was already the case. Next thing we want to do here is we want to click on Analyze, scroll down, go to Linear Regression. Okay, let me read it. Okay, so this is what you should have. So we want to predict stress due to work overload, that is our outcome variable, as a function of anxiety and depression. Okay, that our model is already set right now. What could we want to add? Same things essentially as with simple linear regression. We could have the confidence intervals of the parameter estimates. That can be useful. In plots, we may notably here want to plot the predicted, the residuals as a function of the predicted. This is to check homoscedasticity or homogeneity of variance. Another thing that we may want to do is here have a histogram of the residuals. By the way, and let me click here on continue already, we may also want to save the residuals. So if I click on save, I may want here to save, for example, the unstandardized residuals if I want to check their normality. And finally, we could check that each predictor holds a linear relationship and not some other form of relationship with variable. And to do so, we may here produce all the partial plots, and this will draw scatter plots of each independent variable as a predictor of the dependent variable. So we have everything here. Let's click on continue and click on OK. Okay, so first thing, it is the same really as simple regression. Here we have the R-square, which is the coefficient of determination. It tells us the amount of variance of the outcome that was predicted by the model. And so here, in other words, we could say that the model predicted 23.8% of the variance of stress due to work overload. Is that a significant amount? We can know so here by having a look at the p-value for the f-test of the model. Okay, so here it tells us that the amount of variance explained by the model is significantly higher than 0. Another way to say that is that the model significantly fits the data. Okay, great. If we scroll down, the coefficients, also known here as the parameter estimates, so here we have the intercept, here we have the slope for anxiety, and here we have the slope for depression. Each of these estimates has been here t-tested, and all of them are significant. Right, so in other words, here we see that anxiety has an effect on stress due to work overload, and we can also say that depression also has a significant effect on stress due to work overload. To quantify the effect size, of course, we would use the standardized coefficients with Cohen's rules of thumb that you can find in the slides. Okay, so here, for example, we have a small effect of depression, and here we have a moderate effect of anxiety. We also have the confidence intervals, 95% confidence intervals around each of the b values here. Right? So each of the parameter estimates, the unstandardized parameter estimates. Remember, if we wanted to have the confidence intervals, it's called the beta, the standardized parameter estimates, we would first need to standardize the variables. Okay. By the way, we now see that this R here does not correspond to anything directly in this table, right? It is because it is a multiple R. So here you must not confuse these values with bivariate correlation coefficients, for example, anxiety and stress due to work overload. Right? So these are not here equivalent to bivariate correlation coefficients anymore because it is not the same model anymore. Right? So in other words, this you could do, here have a look at the beta to check the correlation between the IV and the DV. You could do in simple regression. You cannot do it anymore in multiple regression because it is essentially not the same model. Okay, so let us scroll down and have a look at the assumptions now. So here we see that we have, well, a fairly normal distribution of the residuals, which may indicate good conditional normality. Also here there's no tendency that we can see between the predicted and the residuals. The residuals not seem larger for higher predicted values or lower for some predicted values. So it seems like here there is no relationship between the predicted and the residuals, which is a good thing. Here, if I have a look at the partial plots, remember here I'm trying to see if there is another type of relationship than a linear relationship between each of the predictors and the outcome. Here, well, doesn't look like there is another form of relationship. If we wanted to test, so one of the quick ways to sort of explore for a different type of relationship is we could double click on this on the chart, and here if you add fit lines, well, you could try to see if there's another tendency than that. Notably, well, you could check a quadratic tendency here. Doesn't look much better. If you have a look at the R square, it doesn't look like you're predicting much more, right? Here I have 10% variance, and if you fitted a quadratic model, it would be also here. It doesn't look like there's another form of relationship that missed by using a linear model. So here it's essentially useless. If we checked for depression, we'll probably find the same thing. So here, for example, the linear trend explains 5% of this relationship. If we added a quadratic, well, it's slightly better, but it's probably here because of this outlier over here. So it's like really help much. Another thing that we could here check, of course, is we could analyze the normality of the residuals. So if I check the residuals here, that's my new variable that has been created. By default, it's always the last one, by the way. I added it in my dependent list. If I go to plots, I need the normality plots with tests, and well, the histogram I already have. If I click on OK, let us see. So skewness and kurtosis seem still okay, right? I don't really see here that they are out of our rules of thumb or bounds of -1 to +1, so it's still okay here. I do not see a significant departure from normality, so still okay, we should say. Right? So here there is the distribution of the residuals is not significantly non-normal. Remember, it is different to say that, which is actually the case here, to say that the distribution is normal. The distribution is obviously not normal, but it is not significantly not normal. Okay, so the assumption seems to not have been, at least not too violently here, violated, which is a good thing, and which can lead here to say that we can use this linear modeling framework.